Hi all, I realized that there was a minor error in the problem that we worked on earlier that I made up kind of on the spot, and so I wanted to correct that error here and explain it with a video so that you could understand exactly what was going on. You should have these notes uploaded in Sakai, but here we go. So here's the gist. We had this problem where you had ice melting in really hot water, 70°C water, so like a hot tub or something like that. You've thrown a couple of ice cubes in there. We know that Q gained by the ice is negative the Q lost by the water because the water is warm. And so Q enters the ice cube, and then the ice cubes melt, and so they become water, but I'm going to remain calling it ice, even though it does actually change into water here because the mass of the ice is much smaller than the mass of the water in this case. So here's where I made the mistake earlier. I said that the Q gained by the ice splits into two pieces, the melting of the ice and the changing of the temperature, which is partially true, but it's actually, there's a slightly more complicated fold in this, which is that there's actually three pieces here. So if we think about just what's happening to the ice, this is sort of the picture of what's happening to the ice. The ice is starting at negative 35°C. And then it has to raise the temperature. So feel free to pause this if you need to copy this graph down. So it starts at negative 35 and then it goes to 0. So that process happens when this is actually ice itself, right? So the ice has to raise to 0 degrees. So we're just strictly changing the temperature. So that would be Q equals MC delta T. And so MC, and then the change in temperature from here to here, well, the final temperature in this stage is 0 degrees, because we're just looking at these three stages separately. And the initial temperature is negative 35, so it's 0 minus negative 35. In the second stage, the ice melts. So this is Q equals MLF, where the LF is given by the latent heat diffusion for water. So here it's kind of a mix of ice plus water. And then in this third stage, it's all water. And so this is where that folding complexity occurs, because now you actually have the mass is still the same because we're still dealing with the original mass of the ice. So that was that 0.1 kilograms. But now, because we're dealing with water, because all of it is melted here into water, we have to use C of the water. So that's where my error was here. We have to use C of the water. So first stage, we go from ice to, we're remaining ice, but we're just changing temperature, so we use C of the ice. Here we have the slush, so we're just using Q equals MLF, just like we did before. And then here, now it's water, and so we have to use C of water once we're up over here. So that, again, that's where that mistake was, so I apologize for that, but I did want to clarify that. So this is now TF minus the initial stage, or the initial temperature at this stage, which is 0. So we've got two different stages where the ice is changing temperature, and then just one stage where it's changing phase. So we've got three chunks total when we're talking about the heat gained by the ice. So here we go. So this is what that first step is going to look like here. So we've got Q gained by the ice. Again, all three of these stages added up. So I'm going to have the ice raising to 0 temperature, or sorry, 0 degrees. So that's MICI, 0 minus negative 35, so that's what's here. Plus this stage, M of the ice, LF, plus this last stage for the ice, which is the mass of the ice. Remember, we're keeping the mass of the ice in all three of these stages here because we're dealing with the ice side first. So that's ice, C water, T final minus 0. And again, it's C of the water here because at this third stage, all that ice will have melted into water. And that equals negative the Q lost by water, because all the water is doing is changing temperature. And when I say water, I'm talking about sort of the bath, this hot tub that we're putting the ice in. So it's this water now that we're talking about on this side. So just to be clear, all three of these terms here, 1, 2, 3, these are all referring to what was originally the ice cube. And then everything that's happening over here, that's all referring to the water in the bath. Now the rest is really just math, but I'll walk you through it in case you're interested. So I plugged in my numbers, and you'll notice because we have a melting point of 0, you know, MICI times 0, that just becomes 0, so that term drops out. And same thing happens over here when I distribute this. MICW times 0, that just drops out. So that's kind of nice. So now we're just left with MICI times 35 plus, and I'm just carrying this down, MILF plus MICWTF equals negative MWCWTF. I have a minus MWCW times 70. All right. So again, TF is the thing that I'm looking for. So this is now exactly like what we did in class. So TF is the thing that we're looking for, so we want to move all those terms with TFs to one side. So you'll notice over here, I have a TF here and a TF there. So I've literally, all I've done is I've subtracted MICWTF, this term, to this side. And then I've done the same thing over here. I've subtracted MWCW70 to that side. So now all my TF terms are on one side, everything else is on the other. And so now it's just a matter of pulling out the TF, factoring out the TF. So if I factor out the TF, I'm going to get this whole left-hand side again. I didn't bother to rewrite that. Whole left-hand side divided by this business right here, which is MWCW and MICW. They both have negative, so I pulled out the negative. You don't have to be that fancy if you don't want to, that's fine. But this is my expression, and you know, the givens are the same givens that we had in class. They're identical to the givens that we had in class. So when you plug in all of these numbers, and again, you would expect, because the hot water bath is at 70 degrees Celsius and the ice is negative 35, you'd certainly expect the final temperature to be somewhere in between the two. And I would expect it to be certainly somewhere above 0. There's not nearly enough ice here to freeze the liquid water here at 70 degrees. So I would expect it to be above 0, somewhere between 0 and 70. The final answer that I get when I plug in all my numbers to this equation, I get 45.95 degrees Celsius. And just as another reminder, and I mentioned this in class as well, make sure you don't round too much. You don't want to make a silly mistake just because of rounding somewhere earlier on. So there it is. I hope that this is helpful and that it hopefully helps clarify exactly what's going on. Again, just a quick recap here. You still have the Q gained by the ice is negative Q lost by the water. It's just that the ice kind of goes through these 3 stages. Not really 2. It goes through 3 stages. And again, the reason why we couldn't just have it be 2 is because C, the specific heat, is different for ice than it is for water. So you have actually 2, you have to split that up into 2 different stages, with one is sea ice and one is sea water. But this whole time you're using the mass of what we're calling the ice here, what was originally the ice. All right, great. Well, I hope this helps. Feel free to email me if you have any questions or drop by office hours.